All right, in pursuing unification of quantum physics, quantum field theory, with general relativity via Clifford Algebra, also known as the space-time algebra, what I've been contemplating recently is using the space-time metric, which is at the center of space-time algebra, to bring the notion of space-time curvature into quantum physics. So we have the Einstein gravitational field equation with the Ricci tensor and scalar on the left side of the equation, quantifying curvature. And then on the right side of the equation, we have the energy momentum tensor, which is basically the collection of third-degree derivatives of time and momentum with respect to each other. 3 instances of momentum in each of 3 directions, and then time. And then those are multiplied by the gravitational constant in whatever form we're using it. I mean, well, the capital G, right? So if we want to use space-time algebra, which includes concepts of curvature in quantum physics, what do we use as the operator? I mean, it's going to be a space-time metric of some kind. I mean, I wonder if it isn't the Ricci tensor. I wonder if maybe it has to be the full left side of the Einstein field equation that then takes the place of the flat space-time Minkowski metric as the central operator in the algebra. What kind of an effect will that have on the algebra that gets generated as we explore it? I still have my suspicions that what we will find is that quantum field theory interactions, like particle interactions, will still occur in terms of a flat space-time. Maybe there will be some very high-order curvature terms, but I suspect they'll be small enough that they can be neglected. I think that where curvature will add something to quantum field theory is in the propagators. Maybe not so much in the space-time of a particle accelerator, which is relatively small, but more in terms of astrophysics, where we're talking about large distances and gravitational lensing that very well do affect the geodesic paths on which particles propagate. When I contemplate the idea of putting a curvature tensor in as a space-time algebra operator, I get overwhelmed by how complicated that would be. And yet at the same time, it's really an exciting prospect. So I wonder, do we have the computing capacity today to carry out complicated calculations like these? And would the results be relevant with the relatively low energies that we can create in our particle accelerators here on Earth? I suspect they might indeed be relevant when we are looking at things like super energetic particles that show up in our upper atmosphere. And of course, where do we go when we want to study the extreme realms of physics? We go to the black hole. I'll bet you that using operators that include curvature, I'll bet you they would be relevant when we are doing calculations related to black holes, especially the realistic ones, the rotating ones, the ones we observe. All right, so that's where I'm at right now. My plan today, after I get back from the gym, is to look at the next video I have on space-time algebra. And, you know, every day whenever I upload a video more in terms of spirituality and general thoughts, I also try to upload one of these on my very specific thoughts about quantum physics, quantum field theory, general relativity, astrophysics, things that really get my heart beating and make me passionate.